So the next thing that we will discuss is the idea of space-time diagrams and how they will help us visualize the transformations of special relativity. So we will begin by first drawing a set of axes. So the set of axes will look something like this. By convention, we'll draw a spatial axis in the horizontal direction, and we'll call this our x-axis. And this direction we'll call our time axis. And rather than use units of time, we'll use units of c times time. Okay. So for example, if t is measured in seconds, ct is measured in light seconds. It's the time or it's the distance traveled by light in 1 second. Okay, so ct is a measure of time, okay, which is strictly speaking a measure of distance. Now we will visualize the transformations. Since we're drawing it on a sheet of paper, we have no choice but to visualize the transformations in one spatial dimension. Okay. So we're ignoring for the moment the y and z directions because, as we've seen, if the relative motion of observers s and s prime is along, let's say, one direction, which is in this case we'll take it to be the x direction, then the y and z coordinates do not transform. And so the interesting transformation is already going to be represented in our diagram. Now, this labeling of the coordinates of a particular space-time point by its x-coordinate and its time coordinate already means we're talking about space-time coordinates as seen in a particular frame. So in this case, we'll take this to be the frame of an observer S. And we will now take a particular observer who is sitting at the point 0, 0. We'll call this observer O. Now, if you take a particular point on this diagram, you can find out the spatial position of this event and the temporal position of this event by asking what is the x-coordinate, and you do this by dropping a perpendicular down to the x-axis, and this tells you the x-coordinate of this event. Let's call it event A, and this coordinate is xa. And if I want the time coordinate, I would drop a perpendicular onto the time axis, and this tells me what c times ta is. So therefore, I would have located this point as being at a spatial coordinate xa and a time coordinate ta. Okay, so I've identified the time and space coordinates of this point. So this allows me to uniquely define a space-time points, and a space-time point can be associated with events or space-time events. Okay, so if I know the location A as described by this observer, I can tell you when I want to describe a physical processes that something happened at A by telling you what the coordinates of that space-time point were. Okay, so now let's get rid of this. And now let's imagine that we have a particle, okay, a physical particle, and we track the locus of its space-time coordinates as it moves. Okay, so this particle could be moving in this frame S, so it would trace out some trajectory. And the important thing about this trajectory is if I take the slope at any point, okay, if I take the slope of this trajectory at any point, let's say over here, the slope tells me how much distance delta x it covers in a time c delta t, or in a time delta t. Okay, so the slope tells me delta x over c delta t. Okay, so this is the slope. And this locus of points gives me what we call the world line. of a particle. And something important about the whirl line is that for every instant of time, there can only be one spatial position. Okay, because the particle has to be located at one particular location at any instant of time. However, it can come back to the same spatial position. For example, it could go at a future time, it moves from this location to this location, but at a future time, it could move back towards the earlier location that it was at. Okay, so now that we have this trajectory, and this tells us the motion of the particle. We also see another property. Okay, so the first property of the whirl line is that at any instant t, only one x coordinate. Okay, but the reverse is not true. At a given x, you can have multiple times at which it comes back to that same location. Now, the second thing is about this slope. So the speed of any particle instantaneously, v, is the distance it travels by delta t. So this slope is nothing but v over c, where v is the speed of the particle. And this speed of the particle has to be less than the speed of light, so this slope is always less than 1. Okay, which means that all slopes or all tangents to this trajectory have to have slopes which are, sorry, let me just correct this. So it's actually, the slope is this. So the slope is the tan hyperbolic of this angle, tan of this angle. So the slope 1 by m is c delta, m is the slope, and that is c delta t by delta x. Okay, so what this tells you is that the slope is actually greater than 1, which means tan theta, which is m, okay, is greater than 1, or theta is greater than 45 degrees. Okay, so that is the slope of the curve, or the tangent to the curve, always makes an angle greater than 45 degrees because the particle has to be traveling less than the speed of light. Okay, so this implies that the slope of the curve m is greater than 1, or tangents to the curve are always at angles greater than 45 degrees. Okay. In other words, I cannot have a particle whirl line that looks something like this. Okay, because this slope would mean that it's traveling at a speed greater than the speed of light. Okay, so let's erase these things on the diagram. Now, in the limiting case, where the speed of the particle is the speed of light, let's say for light itself, the slope must be 45 degrees. Okay, so for light particles or light waves, the speed v is equal to c, and therefore the slope m is equal to 1, or theta is equal to 45 degrees. So light beams always travel at 45 degrees. Okay, so if I send out a light beam from O, if this observer sends out a light beam at this instant of time, this light beam would always travel at 45 degree lines on this space-time diagram. And this, if it sends out on the positive x-axis, it goes this way. If it's sent out on the negative x-axis, it would go the other way. But these are the only two possibilities for the light beam sent out from O. So these are light beams sent out from O. And the other thing that you can see is since O cannot communicate anything faster than the speed of light, the only future events that, or only future space-time points that O can influence lie within this wedge or this cone over here, if I think of this in multiple directions. So this is called the future light cone of O. Okay, and we can draw this future light cone for any space-time point. This gives you the set of all space-time points that O can influence in the future. Okay, either by sending light signals or anything else. Anything outside, any space-time points outside this light cone, O can never communicate with by sending light beam. Okay, so what that means is if I want to communicate with a space point which is somewhere here, I cannot communicate between O and this space point at t is equal to 0. Okay, so if O learns something at t is equal to 0 and wants to communicate it to his friend over here, he has to wait at least this amount of time before he can send a light signal which would reach the observer who is sitting at A. Okay, otherwise he has no way of influencing anything that happens at this spatial coordinate. Okay, so the future light cone of O tells you the set of all space-time points that O can influence. And similarly, we could also draw light cones backwards. So if we draw them backwards, the light cone looks like this. And now this set of space-time points is called the past light cone of O. And these are all the space-time points that could possibly have communicated with O in O's past. Okay, so if I consider all spatial points at t less than 0, so any spatial point here, for example, at t less than 0, for it to have communicated or sent information to O by the time t is equal to 0, it would have had to communicate at least, okay, this early. Okay, if it communicates any later, that signal would reach O only in the future, okay, at some time over here. Okay, so therefore to communicate with O, the spatial point over here must be sending out signals, okay, at least at this time, okay, or if not at earlier times. So the past light cone of O tells you all the spatial points that can possibly influence O at the time t is equal to 0. All the space-time points, sorry, that can influence O at the time t is equal to 0.